All right, part 5, I think so, of writing our own compiler for our own programming language called Hydrogen. This is what we have so far. You can declare variables, and you can add numbers together, and you can assign them. You can also use variables in expressions like this, and then we can exit out with some sort of exit code. So if we go ahead and compile this, so this will compile it for us, so let's move this over here. And then if we go in the terminal and then find the executable that it makes, we can go ahead and run that and then echo out the exit code, and we get 11, which 1 plus 2 plus 3, 6, so x equals 6, then 6 plus 5, y is equal to 11, so then we exit with 11, which is what we have over here, which is the correct answer. And in that process, our compiler generates assembly, which gets assembled into the final executable using NASM. So there you go. Maybe in the future we will output to an executable directly, like output the actual binary, but I'm not super familiar with that right now. Maybe we'll experiment with that. But I do think that it's quite nice to just kind of look at the assembly like this instead of, I think it would make debugging even more difficult than it already is. So what are we doing today? I want to implement more math operations like multiplication, subtraction, and all that, but that requires us to do something called, well, I mean, we have to deal with the precedence, right? Because if I do something like this, we need to make sure we do 2 times 3 before we add the 1. And that's a bit annoying. It would be so nice if we could just go from left to right or right to left, whatever, and it's just consistent no matter what. And we also have to deal with parentheses. Right, so let's deal with that. And so what we're going to use is something called precedence climbing. And it's actually a pretty cool algorithm. Normally I like to just kind of come up with solutions just on the spot. But this is such a simple algorithm, and it's fast, simple. So like, why not just use it? And there's a really great resource out there on this guy's website, Eli Bendersky's website. Maybe that's how you pronounce that. Parsing expressions by precedence climbing. This is a very short thing. It's not that long. So if you want to know how this works, it's in here, but I'll kind of briefly go over it. It's just a matter of kind of breaking up our expression into sub-expressions with different precedence levels here. So you can see that multiplication has a higher precedence, so it gets broken into its own precedence level here. Same thing with this one here with, is that exponentiation? Ooh, fancy word. Like that, but I don't think we'll have that. I don't think most languages have like an exponent operator. I think like Python. Does anything else have it? I don't know. But so that's kind of the idea. And also associativity. So this is the idea that, you know, if you do addition, you go from left to right versus with exponents, you go from like right to left like this. But I think exponents are really the only ones that do that. So I think for now we'll just not worry about this and just say everything is left associative, meaning that if it's the same precedence level, we'll just go from left to right. If we come across a scenario where that doesn't make sense, then we can modify it, and we'll come back to this. So the idea is that you just have like you have this while loop here, and you're checking the precedence levels of the next operators, and if it's above a precedence, the current precedence, and you do one thing. If it's below, then you do another thing. I think you'll just kind of see how it goes. It's not that complicated, but essentially we'll be able to build our parse tree with doing the right operations first. Or, I mean, the correct operations, not like right as in the right side, right? So, first of all, we need some kind of ability to check if a token is a binary operator, and then we also need to determine what precedence level it is. And that's why in our grammar, in our grammar here, we have these like precedence levels here, because I was getting ready to deal with this. I knew we were kind of going in this direction where I wanted to use this precedence climbing. And in here, we have different precedence levels for different operators. So for multiplication here, we'll have a precedence level of 1, and then for addition, we'll just do 0. Of course, there are more than those two, but we'll just get these two working for now, and we'll see what we can get working. So I got rid of the multiplication last time because I knew I was going to deal with it. So we need to go ahead and add that back, and I don't know if it's in our list of tokens. I don't think so. We can actually just test that by adding in multiplication here, and it says you messed up, meaning that, also maybe we'll fix these error messages this time, maybe at the end too, because you messed up means that you are here, which means that it's an invalid token. So in here, we'll call it, I mean, it's just a star, so I'll call it a star, because maybe it'll be used for other things. So we'll just add it in here. We could probably make this into a big switch case, but I don't really care enough right now to change it. So this is fine for now. Peak.value equals, and then we're looking for a star. We'll consume that, and then we'll push back a new token of type, token type star. We don't need to continue. I realize that we don't, but whatever. I'll clean this up maybe at the end of today, of today's episode. So now this should come with a different message. Yeah, expected semicolon, because it doesn't know that this asterisk is part of an expression. So it's like, oh, this is something different. So you need to like finish that off before you move on to this other thing that I have no idea what it is. So let's go here to our parser, and I commented out here, node binary expression multiplication. And then for our expression, we want it to be either be an addition or a multiplication. So we need to go ahead and do node, we need to do a variant, right? Because this could be multiple things. We can be a node binary expression add, or a node binary expression multiplication. And we'll rename this to var, and I know I need to zoom in. I know people keep telling me I need to zoom in, and I keep forgetting, okay? It's a big monitor. I know you watch it on your phones, but it's a big monitor, and this is really big for my eyes. So, but I'll try and remember. So, we have this variant here, and this needs to be a pointer. Okay, so now we have a warning here, or not a warning, an error, because this is no longer called add. We need to make this var. So that, I don't think this will build just yet. No, it won't, because we also need to change it in our code generation. So we can go in here. But this might not be the correct. So this is where we generate our expression. We were assuming it's addition, but now we actually need to take into account if it's not addition. So we actually need to do like we kind of need to visit each one. So maybe we need to do gen binary expression, const node binary expression, like this. And then we need like a binary expression visitor. And I'm just going to kind of copy how I do it over here. Oops. And this can either be a node binary expression add. So we'll just do add. Or it can be a node binary expression multiplication, like that. And then we can go ahead and call this. So we will do, how do I do it over here? So we'll do binary expression visitor, and then standard visit with our visitor, and then our binary expression variant. Right. Does that do it? Okay, we need to actually do gen equals this. I need to actually type that out correctly. Okay, I think that does it. So then in here we can do, if it's a binary expression, then we do gen binary expression with our binary expression, just like that. Okay. So then in here we can take our add and do this. So we can take our add, get our left-hand side and our right-hand side, and then here we can just assert assert false, right? And then we'll say not implemented. So this should build now. And then we should get an assert saying it's not implemented. No, because we didn't actually change our parsing, right? That's a code generation. So we need to like get here. I know it's in a recursive call chain. Disable this check. Okay, so we need to parse this according to precedence climbing. So again, I don't typically like to just kind of copy things like this, but this is just such a simple and nice algorithm. I think it's just easier to do it like this. So we're getting the left-hand side. And so in this case, Adam is referring to a, in our case, it's kind of like a term, right? It's either an integer literal, so like a number, or it's an identifier being a variable. So that's kind of like the atom, like the smallest piece of the expression, right? Apart from the actual operators themselves. So then you have the left-hand side, and so you compute the atom. So this is essentially saying, okay, take the first term, because an expression has to start with a term, right? So in our expression here, let's actually just take it out like this. So we'll just say auto term left-hand side equals, and then we'll do, I think we have this try consume. Right. So maybe we do a try consume and then token type, and then we want, actually no, we want to parse a term. So we need to do parse term. And this will optionally give us a term. Right, so let's just make this explicit. So we'll say this is an optional, then node term, a pointer. And if we don't come across, if this doesn't have a value, left-hand side dot, if it doesn't have a value, let's just return nothing, indicating that we weren't able to parse this expression. Okay. So then now, after this point, we are sure that we have a term, right? Otherwise, we would have returned. So we have a left-hand side term. So in this case, if we're looking at this expression, that would be our 1. So we have our 1 here. And then we have this while loop. So let's go ahead and create this while loop. And so this is just a while true. So, because we can break out of it later. And over here, we have our current token. And so this is going to be our binary operator. But we don't have to have a binary operator because of an expression could just be a single term, right? We could just have let x equals 1. So we need to see if there even is another binary operator, right? So we're going to get the next token here. So we will do token. I guess we'll just do maybe current token. Current token. I don't know, something like that. And then we will do, I guess it would just be peak, right? It would just be peak. And this returns actually an optional because we could not have any more tokens. So that's an optional token. Okay. And then so now we do some checks here. So first we're going to check if it's none. If it's none, then we just break. So if current token, if it doesn't have a value, then we just break out of here. All right, so that's the first check. That's pretty simple, straightforward. Or if it's not a binary operator. So in order to tell if it's a binary operator, we actually need to, we need a way of telling if a token is a binary operator. And to me, that sounds like a nice, simple little function that I think we can just do in here somewhere. Let's actually do it in tokenization because that's where all the tokens are. So let's go ahead and create a simple little Boolean is binary operator, and let's take in the token type, and this will just be a switch on the type, and then we'll say case. We'll do so plus is 1, like this, not plus plug. Wait, no. What am I doing? Oh, token type. I need to do token type plus. Or a star. Right? Those are the two. Otherwise, we will return false return true. So we return true for these two cases, otherwise we return false. So this is a nice simple little function we can do for this. And as we add more tokens, we just modify this. Okay, sorry for the sniffling. Got some allergies, okay? It's happening, okay? It's always like that. Okay. Where were we? In our parser, we were under parse expression. Okay, so we need to make sure it's a binary operator. So if it doesn't have a value, or is binary operator token type. If it's not a binary operator, then we break. Or, and this is the last thing we have here, this precedence level. Now, if you look in this compute expression, we actually have a minimum precedence here. And this is how this works, because this is recursive. So essentially what we want to do is we want to keep parsing the expression until it reaches some a certain precedence level, and then it will call it with a different minimum precedence level. So in order to do that, I believe the minimum precedence we start with is just the lowest. So in this case, it would be 0, since that's the lowest. So in our compute expression, let's actually include that minimum precedence, and this is going to be an integer, and this is just going to default to 0. All right. Precedence, yeah, save it to dictionary. Okay. Spell checking code. Sometimes it don't work too well. Okay, so if it's not a binary operator, and then we need a way of determining our precedence level. So in here we have it in our grammar, precedence 1, precedence 0, but we don't have a way of doing that in our code. And so I think we'll do the same thing that we do over here, and there is the dog. We'll do the same thing over here, where we'll return a precedence level. But it might not have a precedence level if it's not a binary operator. So maybe we shouldn't do this. Here, let me explain. Maybe we do this. We return an integer, binary precedence of token type, and we'll have a switch on the type. And then for token type, for plus, we'll return 0. For a token type star, we will return 1. And then default, we'll return null. Like that. And then, if it returns null, it's not a binary operator because it doesn't have a precedence. So we can actually just do it like that. So we can do precedence, if minimum precedence dot, what is going on here? Int is not a function or function pointer. Ah, okay, that's already named. Oof. Oh no, this is called binary precedence. I'm just calling the wrong thing. I see. So this needs to be binary, if binary precedence, if it doesn't have a value, we could store this as a value, I guess. Okay, we'll do this, so we don't have to call it twice. We'll do auto precedence equals binary precedence here. And we'll say if precedence dot, if it doesn't have a value, or, I'm alt-tabbing to the wrong page, or if the precedence of this operator is less than the minimum precedence for computing this expression, then we break. So the idea is, it's like if we're parsing this expression here, when we're doing 2 plus 3, and then we get into multiplication, we're now in this multiplication sub-expression where our precedence level is like, I guess, 2 in this case. Once we get back to this minus sign, our minimum precedence for parsing this expression, sub-expression would be 2. This is a precedence of 1. Therefore, we break out of this sub-expression. And so that's kind of what's happening here. So let's go back to here. So if it doesn't have a value, or the precedence is less than the minimum precedence, then we break out of this this while loop. Otherwise, we will continue on. And I keep going to that page. I want to go here. Okay. And if we keep going, so then he asserts here, assert that it is a binary operator. We know it is at this point. So then we get the associativity, right? We're just going to say everything's left associative for now, so we're not going to worry about that. So it gets the current value of so it gets the operator. It gets its associativity and precedence, which we already have. And then it determines the next minimum precedence. And so this is how it does the left associative or right associative. If it's left associative, then it just takes, then the next minimum precedence is a precedence plus 1. So we'll just hard code that in for now. So let's go ahead and do that. I think that should be good. I'm just wondering here, we have this precedence in here, but we're going to need it over here. I don't know if I want to call it again. So I think what I'm going to do is I'm going to have an optional integer for precedence up here, and then just do this. Yeah, and then I can use precedence over here. Okay, so, and then we check if it doesn't have a value that we break. So we know it has a value over here. So we're going to go ahead and determine the next precedence. So next minimum precedence is going to equal precedence.value plus 1. Just like that. And then we get the next token. And then we compute the right-hand side of our expression, which in this case is we're just doing a recursive call with passing in the next minimum precedence. And that's going to be our right-hand side. So, oh yeah, so this is pretty much just consuming the token. So we do need to consume it. We can do that up here. And we don't, well, we do actually need to know which operator it is. So we'll do operator equals consume here. And then we need to construct the correct type of expression. Right, we're in C++, we have a bunch of types for things. You know, he's using Python, which can just be all loosey-goosey on everything. So we do actually need to check what type this is. So we have a type here. So we can do maybe a switch case. So, well, if the type equals token type semi, not semi, plus, then we want to create a binary addition expression. So we want to do, like, take our allocator, we want to allocate a node binary expression add, right? We also need an expression. So we should do above this equals node binary expression. I'll zoom in. I can already hear the comments. So we have this expression here. And then we can do expression var equals add. Like that. Okay. Otherwise, no, we should have done a switch case here. We should have done a switch case. So we should do a switch op.type, and then case, what is the problem here? Case token type plus case token type star, and then we'll have a default. So if it's addition, then we do this. Where, yeah, see, this is a problem because we can't, like, allocate stuff in here correctly. Okay, well, we're going to do an if-else thing. I'm not going to deal with this switch case nonsense. Else if operator.type equals token type star, Then we can do multi equals mallocator, and then node binary expression multi. And then our expression is then going to be this multi here. And we can actually say that our left-hand side is equal to our term left-hand side here as well. But that's an optional, so we need to do dot value, right? No. Maybe not. What do we have going on in here? I see what's happening here. So we do the left-hand side, the right-hand side, and then we can put them together here. I see. So we won't construct this here at the moment. So what we need to do, we have this next precedence level. We need to compute the right-hand side by computing the expression with our next precedence level. So we will do auto expression right-hand side is equal to parse expression with our next minimum precedence. Right. So we have a right-hand side now. Now we need to update the left-hand side. So the left-hand side was previously just a term. But because we have another binary operator here, we actually turn it into like an expression. So if we look at this blank diagram, we have 1. Oh, that's small. So we have 1 here, and let's put in our expression here. So 1 plus 2 times 3. So we have 1 here. Then it looks at the next token, and it's like, okay, it's a plus. Cool. So we have a plus. And then it will compute the next one, which, you know what, let's just get rid of this multiplication by 3 for now. It'll look at the next one and compute the right-hand side. So we get a 2. And so what it's going to do is it's going to, this is coming from, this used to be the left-hand side, and it's doing this. And this entire thing now becomes the left-hand side of potentially another expression that could be something like this, right? So that's kind of what's happening. So, and in here, he's just computing the operation. He's like actually evaluating it, but we don't want to evaluate it. We just want to create the full tree so that we can do the code generation for it. So in this case, we actually need to create an expression for the left-hand side, which is actually this expression, I think. I'm getting all twisted around here. This is requiring serious brain power. So we have expression here, var Maybe we do want to do this first. Maybe we want to do this. And then here we can do add left-hand side equals our term left-hand side. It needs to be an expression. That's the thing. So we actually need to create an expression left-hand side. Node expression. Come on. And then this expression left-hand side var is equals this term left-hand side dot value. And then this takes the expression left-hand side. Okay. And then our right-hand side is going to equal the expression right-hand side, that value. And in here we should actually make sure that if expression right-hand side, oh, this is where we can, oh, we don't have a try consume. No, okay. We need to do if expression right-hand side, if it doesn't have a value, then we weren't able to parse it. And this is, in this case, we're going to have an error. Unable to parse expression. We will clean up all these error messages eventually. Exit with exit failure. Cool. So now we know that it has a value when we get to here. Okay, so now we need to do the same thing over here. So we need to create an expression left-hand side. In that case, since we're doing it on both of these, we could actually just take this out. Like that. Yeah, we could just do that. And then we can take multi left-hand side equals expression left-hand side. Multi right-hand side equals expression right-hand side dot value. There we go. So now if we take a look at what we have here, then we set the left-hand side equal to this expression, which is this expression here. Okay, I see. So what we actually need to do is we need to take this expression left-hand side and probably just pull it all the way up here. Like that. I think. Something seems a little off here, I'm not gonna lie. So we have our expression left-hand side here, which is our term. We're setting it over here. Okay, so then we're resetting our left-hand side to our expression. Except it doesn't like that. Why? Because this is a binary expression. Var. Like that. There we go. That needs to be in the while loop, which it is. Okay, and then once we get out of the while loop, then we just return the left-hand side. Right? Because the left-hand side is an expression, right? Yes, okay. So then we can return expression left-hand side. And we can take all this old code out. Okay, I'm not super confident in this. I think I got it, but not super confident. But let's see. And we have a bad optional access. Oof. A bad optional access? Where? Let's have the debugger help us. So if we go over here, we're under parse expression, of course. Okay. It's this. Huh. I thought we checked this up here. Precedence equals binary precedence, and if it doesn't have a value, we should just break out of this loop. So why are we here? What is this equal to? I don't know. Huh. Well, this is something. This is something. Maybe I need to... Bad optional access. That is strange. Okay, where did it go wrong here? So we have our main program, we're parsing the expression, and where are we at? We're at 4. 1, 2, or 0, 1, 2, 3, 4. We're at the plus. So we're looking for the precedence level of a plus. Our current token should be the plus. Yes, it's a plus. Oh, maybe we also need to say ooh, I don't think I did this right. This needs to be if it has a value. Else, then we break as well. Yeah, that needs to be like that. I did that wrong. Unable to parse expression. Okay. So at least we got further. Where is this unable to parse expression? You know what? Because we need to consume this. We need to consume this first. And then do the parsing. Okay, exit code 11. Wait, why? No, this is our compiler. This isn't our program. So what happened? With our we're generating our expression. So we have some type of issue here. Something must be like null or something. Left-hand side. Contain value. So multiplication, where the left-hand side. Ooh, it's laggy. Oh boy, what is happening? So the left-hand side. Wow, is this nested? Oh boy, can I just get to what it is? Is something has gone. Okay, it looks like I've somehow got into an infinite loop. Is what looks like is happening, which is probably why it's lagging so hard. So I did something wrong. What's new? So, okay, let's see what's happening. So we parse the term. If it doesn't have a value, then we return nothing. Okay, that's fine. Then we create an expression for the left-hand side, so we allocate that. And we set it to be a term. So what we have now, if we want to really break this down into the specifics, we have an expression, which is a term, which is 1 in this case. All right. So this is what we have. And then we go into this while loop. We peek the next token, which is a plus. We get its precedence. In this case, it will have a value because we will have a token. It will have a precedence value, and it will be less than the minimum precedence. Wait, or will it? Or if precedence is less than minimum precedence, this is 0. Ooh, maybe it isn't. maybe what we need to do is do 1 and 2. Maybe we need to start with 0 and then do that. Okay, that's still got 11. So that's still not right. Okay, but it shouldn't. Maybe it needs to be like a big value. Let's just say like 10 because we don't have anything near 10 for now. Okay, expected semicolon. That's at least different. Okay, I think what might be happening, we're getting it into an infinite loop, probably because we're using pointers, and we somehow got into like, we created a loop in our like data structure here. So I think, I don't think anything was wrong with our precedence here. I think what I need to do here is I need to create a separate left-hand side expression for this addition and multiplication individually. I think that's what I need to do. So I need to create an expression. Let's just call it 2 for now because I'm a little confused. So we're going to allocate a node expression like this, and then we'll do left-hand side 2 var equals expression left-hand side var, and then we'll take this and put this here, and we'll do the same thing over here. Something like that. Okay, so that was the problem. I see. Okay, so we need to fix this naming. So what was happening is that we weren't actually replacing the expression left-hand side. We were just replacing the variant inside of it. And so we were creating this loop. So what we needed to do was create a new expression here and just take the var out of it, kind of. So, so we have this expression left-hand side. I don't like having that 2 there, but I don't know what else to name it because it is a left-hand side. So I'm gonna keep it for now. Okay, but we did get to our assertion, which is good. That's where we want to be, where it's not implemented. So this is actually pretty simple. We can just straight up copy and paste this, and instead of doing add, we do multi, and then we just need to do, instead of add, I believe it's MUL. Might be wrong on that. I don't know. Let's just see. So let's run it. And I don't have LD. Ah, interesting. No, I do have LD installed. Invalid combination of opcode and operands. So that might not be how multiplication works. Let's see how we do it. X86 64 multiplication. So what did I do wrong? MUL. Oh, I think it was. I think multiplication is different. It like does something else. It is different. Multiplication. Where is MUL? Yeah. So you give it. So you move something into EAX or into RAX or EAX, whatever. One's 32 bit, one's 64 bit. And then you call multiplication, and it will multiply what's already in the A register with the register you specify. So you don't need to specify both. So I guess one of them has to be the A register, which is interesting. So I think this is it, and I think the solution should just be in racks. Is that the case? Okay. So I actually didn't figure out what this should be. So 2 times 3 should be 6, plus 1 is 7. Then we do 7 plus 5, so that should give us 12. Is that what we get? It is what we get. All right, that's That's pretty awesome. So if we do something, if we swap them like this, let's just do x so I don't have to keep doing math in my head. So in this case, we should have 2 plus 3, so this should give us 5 for x. So if I go ahead and compile that and then run it, we do get 5. If I do multiplication straight across, we should do 1 times 2, which is 3 times 3. You should get 9. So not get 9, because 1 times 2 is 2. This is why I'm a programmer, because I let the computer do the work for me, because I can't do math in my head. Boy, I'm not even gonna cut that out, because I'm too lazy. I'm too lazy. If I do addition, okay, so that seems to all be working. Okay, but let's try if we add 1 after this. So this should be 2 times 3, which is 6. And then it should add the 1 to get 7, and then add 1 to get 8. So we should get 8 here. Okay, we get 8. That question mark is just from this wrapping around. So there we go. Okay, if we look at our assembly, yeah, okay. So if you don't quite understand what's happening, so let's see, what does the parse tree actually look like here? We don't have a way to print these out. Maybe we should have some way. But the idea is that, okay, hello. The idea is that we have this plus here. And let's make these straight lines. All lines are straight though. So we're gonna have this, and then we'll have a 2. So we have 1 plus 2. But we want to do the multiplication first, right? So in order to do the multiplication first, we can't have this structure here. This 2 actually needs to be a sub-expression of a multiplication, where you have 2 and 3. Like this. And in order to do the addition, you know the left-hand side, but in order to do the right-hand side, but in order to do the addition, you have to do this multiplication first, because you need to get this value in order to do the addition. So it does these nested expressions. And if you think about, if you look at how the precedence climbing actually is visualized here, you have nested sub-expressions of different precedence levels. And we have our parse tree here, which is different sub-expressions where the further you go down, the higher the precedence level. So it really like corresponds like 1-to-1 like perfectly. So that's why precedence climbing is just perfect for generating these parse trees. And because of the way that it works, it's so easy to add more operators, right? And add more precedence operators, or precedence levels. There is a way to do this without precedence climbing. You can just directly like encode it into the grammar itself by having different productions that represent different precedence things. But if you want to add to it, it gets really messy, because now you need to modify a whole bunch of productions. And then our productions correspond to our, we're just handwriting our parser. So whenever we mess with our grammar, we need to mess with our parser and then mess with our code generator. So it's like, every time we mess with our grammar, everything has to change. And so the less we have to change, the better. So just having this precedence climbing for our binary expressions is really great. So let's actually add some more binary operators to see if things actually work. So in this case, what we want is subtraction and division. Okay, and these actually depend on order. They're not commutative. So we'll find out if we're doing the correct order of left-hand side and right-hand side in our code generation by seeing if this still works. So over here, we have multiplication here and addition. And I wish this would stop scrolling, but that's okay. We'll do subtraction here, and then we'll do division up here. Maybe we'll do, this doesn't really matter because they're the same. We'll put that over there. And then these will both have 1, and this will both have 0. And I think during the process of debugging, I went over here and I changed the precedence Where is it? Where is it? Oh, it's in tokenization. Yeah, this can be 0 and this can be 1, and that should still work perfectly fine. Yeah. So now what we need to do is we need to add sub and div, right? So sub and div. Okay. Need to make the font bigger, otherwise people will complain. Else if peak.value equals this, then we'll consume tokens.pushback type equals token type sub. Don't need to continue. I'll swap this to a switch statement at the end of the episode. I know I can already hear the comments, and even though I'm saying it at the moment, people are still writing the comments. I wasn't expecting, the first video actually has above 100,000 views already, which is pretty cool. But I will be honest, the majority of the comments are good, and most people enjoyed it, which is actually really not what I was expecting, because this is so niche. But there are a lot of people that just have some really bad opinions in the comments. Sorry guys, but the majority of you are fine. Some people, whew, it's I'm not deleting any comments. I don't really care. I'll leave it all up. So, but some of them are interesting on the videos, So, okay. So we have subtraction and we have a division. Okay, so now we need to add it to our tokenizer. We need to say that they're binary operators, right? So we have, we need to give them their precedence. So our plus is going to have the same as our subtraction. And then our division is going to have the same as our star. Okay. And, okay, so that did that. But now we actually need types for these, right? So we have add, we have multiplication. Now we need subtraction and division. Now, I can already hear the comments. Why don't you just make a node binary expression, have the token which represents the binary, which represents the expression, right? Why don't I just go in here and just do like token op, and then just have this be like binary expression? Because then you don't get static analysis for our match statement, our match statements, aka our variant visitors. It's some extra safety, and I'm the most safe programmer there is, so we're gonna keep doing it this way. Yeah, that's yeah, I think it'll be a little safer. As things continue to change, I think it'll just, having types for everything means that our compiler will be able to perform much more static analysis than if we just did runtime checking of, well, I guess it's still runtime checking, but at least it's doing some kind of static checking here because of our variant, right? Because in here, as soon as I add node binary expression subtraction, and then node binary expression division, it's not going to compile, right? Because we're not visiting all these different types of our variant. So you do get some type checking here versus if we were just checking what type the token is. That would be a runtime error versus a compile time error. So, but honestly, I'm not super opinionated here. I really don't care that much. Whatever works, works. And this is all for educational purposes anyway. So we're going to continue with it. So under tokenization, just kidding, under parsing, no, just kidding again, it's under generation. The loss of train of thought is scary. And we need to do subtraction. So void operator const node binary expression subtraction sub. All right, we got an extra p in here. You don't want the extra p. Okay, we'll do addition here, sub, and we will see if this is the right way around. One thing though is that we can't actually test negative numbers because, well, first of all, it's not part of our grammar. But but even if we could do like, 5 minus 10, and we exited with that the exit code, which many people have commented already, is only uses 8 bits of the register. Even though it's a 64-bit register we're returning, it's only reading the first 8 bytes. 8 bits, I mean. First 8 bits. So it's not actually going to display a negative number for an exit code. Unless we use a smaller register. Maybe, I don't know if it's signed or not. I don't know, can you have negative exit codes? Maybe if you can do like the 2's complement thing where it starts with a 1. Maybe. I don't know. Can you have a negative exit code? Let's just Google it. Can you have negative exit code Linux? It's unsigned from 0 to 255, so yeah, it's not going to happen. Okay, so let's try this out. So let's do 3 minus 2. That should give us 1. Okay, we didn't visit everything still. Even though, yeah, we still need to have a node binary expression division. We still need to have division here. Oh my goodness, I can't type right now because I mistyped here, and now all the stuff ain't working. Okay, I'm just taking a guess that this division works the same as multiplication here. So we'll just try that. And whenever we get to it, and we'll see. Okay. Exit code 11. That's not a good sign. That's not a good sign. Ooh. Why? You know what? Sanity check. If I do 1 plus 2, does this actually work? Yeah, this works. We get 3. But if I do 2 minus 1, that doesn't work? That's strange. Oh. Under our parser. See, this is why I like static analysis, like compile time checking. Because in our parser here, we're just doing an if-else on this. Yeah, see, we're just doing an if-else, checking what token type it is. So this is the exact same thing I was talking about. If I did this during code generation, we just get like an error, a runtime error. But unfortunately here, I don't think we can't do any static time checking with this. But this is the issue. So you know what I should do is do this, and then I should assert false. I should make this unreachable. So at least it gives me an idea of where this is. And for some reason I don't have this included in here. So now this should get me to the assert. Yeah. Because we need to go through all of these here. These all look pretty similar too. Again, indicating to me that maybe I shouldn't have separate types for all of these. But I'm doing it anyway. And the commenters will be unhappy. But I, in my own soul, will be happy. So, sub. And we just need to change this to sub, which I can do with a Shift F6. Sub. And this needs to be node bin expression sub. And then we need an else if for div. And then do a Shift F6. Div, I have a stupid keyboard tray. and I can't really see the top row of my keyboard, and I don't quite have the muscle memory to know where the F keys are, and so I have to like look underneath the desk inside the keyboard tray to find the F keys, which is a little annoying. Oh, I already have div. Why? What? I already have div? Where? I don't think I do. CLion, you don't know what you're talking about. Go home, you're drunk. Okay. Node binary expression div. Okay. This will build. Will it run? Okay. Do we get a 1? We got a 255. What did I do? 2 minus 1. Okay. I think it's backwards then. We probably did 1 minus 2. So that will give us 1, won't it? Yes. Okay, so it's backwards. That means everything's been backwards, but because, you know, addition and stuff, it doesn't matter. So what we actually need to do is swap these. So we need to do, I think we need to do something like this. I mean, we could swap this any number of ways. This is probably just the easiest way to do it. Just to swap these around like this. I'm sure there's a keyboard shortcut to move lines. I know what it is in VS Code. I don't know what it is in CLion. Oh! It's Alt-Shift. Yeah, now I know. Okay. So now we should be getting... Okay. So if I do 2 minus 1... 2 minus 1. Also, this needs to be over here too, because I keep switching away. Okay, that's good. 3 minus 1. Oops, I need to compile it. Okay. And let's do something like 10 minus 2 times 3. So then this should do 6. 10 minus 6, that should give us 4. Which we get. Okay. And then after that, let's divide it by 2. So what this should do, 2 times 3 is 6, then divided by 2 is 3. 10 minus 3 should give us 7. Is that what we get? It is. Cool. What we don't have are parentheses, right? What if I wanted to do this? Invalid expression. That's not valid, according to our grammar. This is actually a pretty simple thing that we can fix. Yeah, this is actually pretty easy to fix. Basically, when we see parentheses, it's basically like resetting our precedence climbing, and we're basically starting from the beginning. And we're parsing everything in that sub-expression in those parentheses. Because parentheses are essentially like highest precedence level. Like nothing goes above parentheses. It's the highest. So we can just reset the precedence climbing. So parentheses are actually treated as like a term. So in our term here, what we can have an integer, literal, and identifier, or we can just have in parentheses another expression. Something like that. And that'll do it, I believe. So, what should this be equal to? 2 times 3 is 6. 10 minus 6, 4, divided by 2. So this should give us 2, which it doesn't right now, because it doesn't even compile. So what we need to do in our... We already have left parenthesis and right parenthesis, right? Open paren, close paren. Okay, perfect. So we don't need to modify our tokenizer. But under our parser, we need to go find our node term. And it can be an integer, a literal, or an identifier. But now what we need to do is we need to do a node term. Let's do parentheses. Node term like a parenthesized expression. So then we'll have the node, node expression. which isn't defined, so we can do that. Okay. And then for a node term, we can now add that. So node term paren, just like that. And now we should get a compile time error, right? Perfect. Because we're not visiting all of the possible combinations. And so now in here, we can have a const node term paren, paren, const. And then we will just do parse generate expression term paren expression. I think that's it. It's not it. Really? I thought I had it. I thought I had that one. Oh man. Wait, we didn't modify our parser. I just noticed we need to do. We actually need to modify our parser. So we need to else if auto. Oh my goodness. Open paren equals try consume token type open paren. This is okay. And then we need to create an expression. No, because we're gonna parse for one. So so we need to actually do is auto expression equals parse expression, and then if we need to okay, and then if expression, if it doesn't have a value, then we output an error saying expected expression. We exit with exit failure. And then we need to try and consume the token type close paren. And then error message, we put expected close paren. And then term, we need to allocate a term. Right, so we need to auto term equals allocator allocate a node term. And then we need to do term var equals expression. Oh no, we need to actually do one of these. Allocator allocate node term paren, and then we need to do term paren expression equals the expression, and then equals term paren. And this needs to be dot value. And then we can go ahead and return the term. Okay. Is that better? We get 2. Yeah, things are getting a little messy. This could probably maybe be solved with some type of inheritance. Maybe, I don't even know. But, you know what? Part of me kind of likes this explicitness. Because it's just so clear. You know exactly what's happening. Like, everything has its own type. You have an allocator. You're doing all the allocations explicitly. We're visiting everything explicitly. We're doing it with our, like, match statements during our code generation. You know, I'm sure some people are like, this is bad code, but I don't really think so. You know? I think it's pretty easy to tell what's going on here. Right, I think it's pretty readable. We try and consume an open parentheses. We parse an expression. If we weren't able to parse it, then we have an error message. Then we try and consume a closed parentheses. If not, then we throw an error message. And then we go ahead and allocate our AST nodes and set them appropriately, and we return them. Yeah, I think it's pretty straightforward. It's a lot of lines, but I think it's readable. So I'm fine with that. But I do think we need to go to our tokenizer and actually make this a switch statement. I do think that would make much more sense. Instead of this if-else thing. So what we should have is a switch. But we keep calling peak.value. So what we need to do is have like a char c equal, oh no, is it peak.value? Right? If peak.has has value, then we take the value of it. And then we want to do a switch on c. And we want to say case. Can I do is alpha on this? Is this like a valid thing I can do? Okay, it's not a constant expression. See, that's probably why I didn't do that. Yeah, because switch case, it requires these to be constant. I could probably do something to get around that, but yeah, okay, we're keeping this. But I think it's pretty clear we don't need the continues in here, because this is, we're doing else if. If we were just doing ifs and not else ifs, then we would need these, but we don't. So we can get rid of these, and we should be okay still. Oops. So we'll clean that up. Oh my goodness. Okay. That should be good. Still good. Okay. So that was a pretty, I think that'll probably do it for today. I was going to see if I wanted to get to error messages, like proper error messages, instead of just saying you messed up. But I think we'll do that next time. We'll take a break from doing these fancy grammar stuff and kind of let it sink in a little bit better. The source code is up on GitHub in the description if you want to look at it. But I think that will do it for today. So I'll see you next time. Bye.